All right, so let's see. I think I should say a few more things about neutrinos, and then I'm going to say some things about anomalies, which are confusing subject. Okay, so first of all, the matrix of the CKM matrix, which acts on the down quarks, so that the sextet of quarks is UCT and then V on DSB. That's what goes into the covariant derivative. This V in absolute value, maybe I should write it like this. The matrix of absolute, the matrix V, of course, is unitary and 3 by 3. But if we just write down its absolute values, then what we get is, the online notes have all the figures. I'll just write 2 figures. Well, 3 in some cases. Well, well 225. Might as well put this now 74. Okay, they look like this. I may have put in an I delta at the last. Obviously, if we're talking about absolute values, you don't want any I delta. There are 3 angles that one conventionally associates with this matrix. They're called alpha, beta, gamma, but there's only one actual complex phase. And if I wrote this so that it was a 3 by 3 matrix of complex value, complex numbers, would be an e to the minus I delta there, and then there would be e to the plus I delta buried inside these complex numbers in a complicated kind of way. Let me tell you what the alphas are. Alpha is the argument of, in fact, I've got the wrong glasses on. It's the argument of minus VTD V star TB over VUD V star UB. And the idea here is that we have CT going this way, and the other one's DST going that way. So that's how we label the matrix elements. And so that's that argument. There's another sign beta that's minus the argument. In other words, this is a ratio of complex numbers, and it has a certain phase. And this is basically the angle of the phase. So this is argument of, or minus argument if you want, of VCD, VCB star over VTD, VTB star, and then gamma is argument of minus VUD, V star, UB over VCD, V star CB. Okay, now these numbers have, these angles have been measured to some extent. First of all, they add up to 180 degrees. So alpha plus beta plus gamma is 180 degrees. And decays of B-mesons into pi, rho, tells us that alpha is 85.4 plus or minus 4 degrees. So it's nearly 90 degrees. Gamma, well, let me tell you how you get gamma. B plus or minus going into the D meson and K plus minus, that gives you the gamma is 68.0 plus or minus 8 degrees. And so beta is about 26.6 degrees. I'll try to work out the error. So these are substantial angles. Maybe I should say something about these mesons. The B meson is a B quark and something else, some anti-quark. So it could be U bar, D bar, S bar, whatever. And these are the various light B's. The D quark has some charge. I think D is CS, isn't that right? Where we have ambiguity here. CS bar, of course. I think that's what we're talking about here. I've actually forgotten. Anyway, let's see. Okay. If we have the simplest way of thinking about the neutrino masses, of course, is to say that they're actually right-handed neutrinos, and then you can have simply a Dirac mass matrix for them. And we were talking about that before. It was something like a sum on ij, iv over root 2, c nu ij, nu bar left, flavor I, nu flavor right, j, plus Hermitian conjugate. And so then the neutrino mass matrix is iv over root 2, c nu ij, and we can rewrite m nu as L nu sigma nu R nu dagger. And we would do the same thing with the electrons, and what we can do in any particular, let me see if I can do something about the noise here. So we have class. And so normally we talk about the CKM matrix for the leptons. We would normally say it's L nu dagger LE, where the LE came from the same singular value decomposition of the charge lepton. But we normally, as with the quarks, we decided that we would identify mass and flavor eigenstates for the up quarks, and then we would, these are all mass eigenstates, and these then become the flavor eigenstates for the down quark. Similarly, for the leptons, we could do that, but we're so used to thinking about the charged leptons as having mass and flavor, as being sharp in both mass and flavor, that instead of making the And of course, let me write down what the sextet is. It's nu, and then E mu tau, because the charged leptons are in the bottom part. And so what one has I'm getting right. Okay, these are the mass eigenstates, and so to get to so these are all mass, and these are flavor. And so what we do, so we would put the V here, but we know we don't want to do that. So instead we put V inverse there. And so for the neutrinos, the CKM matrix then for the leptons is a 3x3 unitary matrix on the neutrinos, and instead of being this, it's the inverse of that. So it is L nu LE adjoint. So that's actually the neutrino CKM matrix. And of course, these matrices, we have a 3x3 neutrino matrix, which would be there. So this would be the sextet of leptons. We have that unitary matrix V nu, whether or not there are right-handed neutrinos. It's just that we know there are massive neutrinos. The simplest way to have the massive neutrinos is to have right-handed neutrinos, to have Dirac mass terms. But of course, we can also have, for the right-handed neutrinos, we can also have Majorana mass terms, which would be nu transpose I, a sigma 2 acting in the on the Dirac or Lorentz indices, and then a nu right J, and then some, I don't know, C tilde, maybe I could call it C right IJ, C right nu IJ. This would give another mass matrix. Notice that this is also gauge invariant because the right-hand neutrinos don't participate in the gauge interactions. And so we would, if there are right-handed neutrinos, then presumably this mass matrix comes both from a Dirac term and from Majorana term, presumably. All of them, one set may be all zero, and it's just not known. If there are no right-handed neutrinos, then it's hard. Then there's no easy. If you just have left-handed neutrinos, there's no easy way to get mass. It's all kind of beyond the standard model mass. One thing you can do is this. You can say, here is our doublet of lepton fields. We can put in a triplet of Higgs fields. This is a new Higgs field. And then we can have two sigmas. Okay, now this is terrible because it violates lepton number. Well, yeah, it can be gauge invariant if this has the right quantum numbers, but it violates lepton number. I mean, this one does too, but these guys are neutral. On the other hand, there are electrons in here. And on the other hand, if phi is has the right quantum numbers, then there's a doubly charged phi here, so you're not really breaking charge. you're conserving charge. So this is a possibility. Another possibility that people talk about is just having the ordinary Higgs doublet with an adjoint, and then EL, and then essentially taking the square of that and dividing by some huge mass. So a term like this is not renormalizable. Well, when I wrote it like that, I think that was a mistake. I think I should say dagger. All right, that's a better expression, at least. I think that's a better expression. Okay, so this term is not renormalizable because the dimension of it's a fermion field squared with 2 Higgs fields, and that means it has dimension 5. That's why you divide by a big mass, lambda. So this could come from some, if there were some fields that were very heavy, that were interacting, and we would then get a term like this with something else in the denominator here, and we'd say, well, this was, we can ignore the heavy fields because they are too heavy to excite as in or out states. They can occur as intermediate states. I'm a little puzzled how it can occur as an intermediate state as 1 over lambda, though, because all propagators are 1 over mass squared. But this could be a heavy fermion that could go across here. So the diagram might have been, there might have been some heavy fermion in the higher theory, and this is 1 over p slash plus or minus m plus m. Okay. But as you can see, we're sort of stretching. Neither of these things is particularly simple or attractive. And what's much simpler is to say, well, there are right-handed fields. That seems to me that it's pointing at at other fields that interact with right-handed quarks and leptons, and we just don't know what they are yet. They might be part of dark matter. On the other hand, it could be something much more like this. We just don't know. And so it's rather complicated. It's mysterious, simply. This matrix for the neutrinos, the standard way of writing, one way of writing it is this. Cos theta 2, 3, sine theta 2, 3, minus sine theta 2, 3, cos theta 2, 3, and then times cosine theta 1, 3. In fact, this thing that I'm writing out, you may say, why is he doing that? Well, that is also one way of writing the CKM matrix for the quarks. And it just gives you 3 different angles, theta 1, 3, theta 2, 3, and theta 1, 2. Anyway, this one is that. Then we have a 0, sine theta 1, 3. And now we have an e to the I delta, 0, 1, 0, minus sine theta 1, 3, 0, cosine theta 1, 3. And then finally, cosine theta 1, 2, sine theta 1, 2, minus sine theta 1, 2, cos theta 1, 2, 0, 0, 1, 0, 0. Okay, so if the mass terms are Dirac, then that's the neutrino mass matrix, and it has this phase like that. If, on the other hand, there are actually Majorana mass terms, then there's another mass matrix, there's another 3 by 3 matrix. And it has 2 more phases, and they're called alpha 1, 2, and EVI alpha, well, 3, 1, that is what it's called. Okay, so that's the neutrino CKM matrix. And these alpha phases are there when we have, if the neutrinos are 3 Majorana particles, then we have these alpha phases. All right, let me say something about the limits on these angles. These angles can be measured to some extent because they occur in neutrino oscillations. So you measure you start out with an interaction and out comes a neutrino of a particular flavor. And then that neutrino of a particular flavor is then actually a combination of 3 mass eigenstates. The 3 mass eigenstates propagate and get different phases. Then when you finally do a detection, what you mostly are detecting is a flavor eigenstate. However, there are some detectors that are insensitive to flavor because, or at least are sensitive to all the flavors because they're sensitive to a Z0 exchange, and the Z0 couples all. Okay, so what are the angles? What are the experimental limits on the angles? And they're really quite striking. It's sine squared of 2 theta 1, 2. Now you see why I wrote these things out, because that's the theta 1, 2. Otherwise you wouldn't know what it was. And this is 0.846 plus or minus 0.021. And then the sine squared 2 theta 2, 3. Okay, this is pretty amazing. It's 0.999 plus 0.001 minus 0.018. This is for normal mass hierarchy, which is to say, that's normal mass hierarchy. The other case is sine squared 2 theta 2, 3 is, and now get a load of this, 1.000 plus 0.000 minus 0.017. So this is the case where you have that, the inverted mass hierarchy. And then finally we have sine squared of 2 theta 1, 3. And this is much smaller. It's 0.093 plus or minus 0.008. So 2 of these angles, theta 2, 3 is almost pi over 4. And pi over 4 means equal mixing. Whereas pi over 2 would mean everything is in one flavor rather than the other. And theta 1, 2, it's not quite equal mixing, but it's close. So let me show you what these mean. I'm borrowing here one of Shashank's slides. So let me do the 2 mass hierarchy cases. We've got first M1 squared, M2 squared, and then way up here, M3 squared. And what are these masses as linear combinations of flavor? Well, this one is about 2/3 electron, maybe, and then 1/6 muon, 1/6 tau. So that's the lowest eigenstate. The next one is something like, I would say, 1/4 electron and I had these worked out and I edited them into something, but I didn't print it out. All right, let me do it very roughly. 1/6, 1/3 muon, 1/3 tau. It's not quite right. And then this one is something like 1/6 electron, 5/12 muon, 5/12 tau. And this one, all right, this is, hey wait, this, I've got these wrong, don't I? Because this doesn't add up right. So this would be, that's 1/6. This would be 1/3, but it's, oh, all right, I don't know. It's a little less than 1/3, but something like that. Then in the inverted case, what we've got is, we've got m3 squared, m2 squared, and then down here m1 squared. And now m1 squared is essentially half mu, half tau. This one is something like 2/3 electron, maybe 1/6 mu, 1/6 tau, and these are just estimates. And then this is basically E over 3, mu over 3, tau over 3. So those are the combinations. In any event, the mixing is very strong, especially the 2-3 case. So this particular one here is, and this matrix, of course, takes 2 into 3, but again, everything's been mixed up before you get to it. So that's a picture of what is going on there in the case of the neutrinos. All right, now anomalies. I tried very hard actually to produce something simple about anomalies, and I just was unable to produce anything simple. So what I'm going to give you is the bottom line rather than the actual derivation. The best treatment of it is actually the original treatment dating back to, I think it was 1979 or so, by Fujikawa, a Japanese physicist who worked out, what he did was he showed that the measure in the path integral, when you had chiral gauge theories, the measure wasn't invariant, or would not in general be invariant. So in other words, what you've got is you've got something like e to the minus s, and remember, one way of doing things is you just integrate over all the gauge fields, and if you're talking in terms of Dirac spin, then you basically are doing this. Now, if you're integrating over all the Dirac fields, it's invariant or typically invariant, and everything's fine. But if instead what you've got is a chiral gauge theory, so that so that you have to pay attention to just the left or right-handed part of some of these fields. Then it turns out that measure's not invariant in some cases. And so let me give you the bottom line for this. It's basically that, and I'm going to consider several different cases. The first case is just to look at U1 of hypercharge. And you remember the quantum numbers for the various particles are quite curious. They are y will be, let us say, -1/2. This is for nu e left, the doublet. -1 for the right-handed electron. 0 for the right-handed neutrino, if there is one. So the neutrino is not going to, right-handed neutrino doesn't play a big role here. Then what we've got is 1/6 for each of the quarks, UD left-handed. 2/3 on the other hand for the right-handed quark, up quark, and -1/3 for the right-handed down quark. And so I remarked at the end of the last lecture that these were really very bizarre numbers. And the remarkable thing is that the anomalies, or the lack of invariance in the path integral, goes away when we have this bizarre assortment of charges. And so what that seems to mean to me is that this obviously can't be the whole story, because it's such a lopsided set of numbers. But on the other hand, because of the success of the standard model and the fact that I'll show you there's several anomaly conditions that just go away, that just the anomalies vanish because of these peculiar combinations of charges. It must be that what we're seeing here in the standard model is like the tip of some huge iceberg that's beautifully symmetrical, but the part that we see isn't. In fact, if we just saw the tip, we'd say, now how can that float? Well, of course, we're missing the part of the ice that's underneath the water. I don't know what to say, but in other words, there's something going on, and maybe after a few years of running at the LHC, we'll know what's going on. Anyway, these charges, together with the T3 assignments, which are implicit, here being ±1/2, ±1/2, 0 elsewhere, give us the right charges for the physical particles, which themselves are a little bit bizarre, because the electron is charged -1, neutrino has charge 0, up and down quarks have charge 2/3 and -1/3. So those are an odd group of numbers also. Okay, the condition that the measure be invariant under U1, and in terms of Feynman diagrams, what you've got is this sort of a situation. It's called a triangle diagram, and it's a diagram where you have 3 gauge bosons. A process with 3 gauge bosons. And what you can see if you work this out is you can see that there's a hypercharged current, and what is it proportional to? Well, the divergence is the sum over the left-handed fields of the hypercharge cubed, and that's because you have the hypercharge occurring 3 times. So these are 3 B's. 3 gauge, the B, the generator of the U1. minus the sum on the right, and then other stuff. And by the way, Schwartz's second chapter on anomalies has serious problems. Anyway, if you look at the latest set of errata, you'll see that he provides a whole new section 30.3. Anyway, G prime squared, 32 pi squared, epsilon mu nu lambda sigma B mu nu B lambda sigma. Okay. So, this actually vanishes. Let's see why it vanishes explicitly. So we want this to be equal to that. So the sum L of YL cubed, what is it? Well, we have two left-handed leptons. Each one has charge minus a half. So that's 2 times minus a half cubed. Then we come to the left-handed quarks. They're over here. They have hypercharge 1/6. On the other hand, there are 2 times 3 for color, so there are 6 of them. So this comes in as 3 times 2 times 1/6. 1/6 cubed. Okay. And what is that? Well, that is minus a quarter plus 1/6 squared. And if you use heavy-duty arithmetic, you can find out eventually that that's minus 2/9. On the other hand, the sum of R of YR cubed, what is that? Well, that is, there's minus 1, and then there are these guys. And so we have minus 1 cubed plus, now we're just doing right-handed, so we've done this one. So we have 3 times 2/3 cubed plus 3 times minus 1/3 cubed. So this is 3 times 2/3 cubed plus 3 times minus 1/3 cubed. Okay, this is minus 1 plus 2 times 4/9 minus 1/9, and remarkably minus 2/9. So the two things are equal, and the Y1 anomalies cancel. And you can see these are really non-trivial cancellations. Now, if we have more generally in non-abelian theory, if we have, say, gauge boson A, C, B, like that, and then we also have this term. A, B, C. And this turns out to be proportional to a trace of TB, TC, TA plus trace of TC, TB, TA. And so this is the trace of the anti-commutator TA with TB times TC. And this is something, if we take, divide by 2 for some reason, and call this DABC, this is called the anomaly coefficient, I guess. And so these T's, of course, are the generators of the gauge bosons that are interact, of the groups, of the Lie algebras that are associated with those generators. This thing you see is certainly symmetric in AB and the trace is symmetric in C. This is totally symmetric. There, I've done 2 de Blasio. She was quite right, actually. Are there any questions? I need to get a drink of something. Questions? All right, I'll just carry the water with me. All right, let's now consider the possibility of an SU3 boson. I'm just using this part of the blackboard because it's there. So suppose this now is SU3, and this is U1 of hypercharge. Now, in this structure here, we've got something a little bit simpler because the hypercharge doesn't change when you change the SU3 quantum number. In other words, over here, the hypercharges are the same no matter what the color is. So there isn't any interaction there. And so when you form this D, what you can do is you can consider trace of, say, TA, TB, where these are SU3, and then you have a Y there. And this is effectively the identity operator, so you can factor out you can factor out the SU3. They simply totally commute. And so this is effectively a delta AB and then a trace of Y. And so now you have to compute what the trace of Y is for the left and the right. So it's like doing this but without the cubes. But we're only doing it for the quarks. So what you have then is sum of L is 3 times 2, and this should be then the hypercharge for the left-handed quarks, that's 1/6. And now the sum on the right-handed ones, well, what are the right-handed ones? Well, over here, what we've got is we have 2/3 times 3 and minus 1/3 times 3. And so this is 3 times 2/3 minus 3 times 1/3. And so this thing is 1, and over here what we have is 2 minus 1, which is also 1. There's heavy-duty mathematics here. But you notice that it's coming from the fact that these things work out is kind of amazing. All right, next we've got, how about SU2 left? SU2 left, U1Y. Okay, now what we've got is something like trace. Well, again, it's TA. And now for some reason I did it differently. I'm going to do it the same way. And once again, the hypercharge, you see the hypercharge doesn't vary with the SU2 quantum number. Whether it's plus a half or minus a half, it's still minus 1/2. And over here, whether it's plus a half or minus a half, it's still 1/6. So this winds up again being just, and then trace of Y. And so once again, we're doing a sum. So the sum over the left are y, y left and but now, let me see, now we're doing, I'm a little confused actually. I've got this guy here, minus a half. Oh, that's right, we're doing the left-handed ones. So we've got 2 times minus a half, and we're just doing the left-handed ones. So the other left-handed ones are 1/6, but now we have 2 times 3, 6. And so what we've got here, just doing left-handed, everything is 0. So it's minus 2 times a half plus 3 times 2 times 1/6, and that's also 0. Okay, so what one can also say is that this thing is saying basically that 0 is y leptons plus 3y quarks, in a sense, and this tells us that this gives us that the charge of the electron is minus the charge of the proton. Effectively, it implies that. Now,
Kevin, I'm sorry. I missed on the DABC
all right,
example
let me get you a candy first.
how the anomaly went away.
Okay, so say it again.
I missed how the DABC, how that anomaly went away. Or
Where?
exactly. I thought the DAB equals 1/2 the trace of TA of those
The
generators.
anti-commutator times TC.
That goes to 0 then?
That has to be 0.
That's 0. Okay.
Yeah. And if we're doing 2 SU3s with 1 hypercharge, well, the hypercharge doesn't vary with the SU3 indices. So you can effectively factorize the trace.
Okay.
And so this just gives you delta ABs, and then you just have trace of Y. So you wind up just with trace of Y.
That's why we did the high power mathematics.
That's why we were doing that. And the same thing happened for SU2, but even more easily.
Okay.
You might say, well, what if you had 3 SU2s? Well, there's something special about SU2. It's said to be a safe group. And in fact, if you just think about it, trace of sigma A, sigma B, anti-commutator, sigma C, well, this is always 0, because the anti-commutator of 2 Pauli matrices is the multiplicity of the identity, and the trace of every Pauli matrix is 0. So that thing is gone just immediately. Okay. Now, if we went through this, we could imagine different theories, theories at higher energies or more general theories, and in fact, looking at the standard model, because things are so lopsided, we're bound, and because of the neutrino mass issue, namely you've got to have right-handed neutrinos, which mean there's a whole right-handed sector lurking somewhere, which may have something to do with dark matter. Or you introduce these weird left-handed mass terms, which are kind of weird. So there's more out there. You can imagine then having gauge bosons coupled to baryon number or lepton number or something else. Well, it turns out if you couple them to baryon number and then you do an anomaly analysis, you find out there's an anomaly. If you couple them to lepton number, you do an analysis, there's an anomaly. However, if you couple them to B-L, then there's no anomaly. Okay? So in other words, in the interaction term in these, normally we write things this way. Psi bar d slash psi. Okay? Well, we can rewrite that as the free part, psi bar d slash psi, plus some a mu psi bar a mu a ta, maybe I'll write ta slash, okay, to put the gamma matrices back in. Well, we could call this, I shouldn't have done that because I want the gamma matrices there. Gamma mu ta, say. Well, we can rewrite this as a mu a j mu a. So the current, so when we, in other words, in these gauge fields, there are currents lurking everywhere. The current is psi bar gamma mu, some gauge generated psi. And what we found is that the currents that occur in the standard model are non-anomalous. But if we made this current baryon number or lepton number and coupled it with a gauge field, we'd have an anomaly. But if instead we have a gauge field coupled to a current that is B minus L, non-anomalous. You can also see that in the actual universe, the mean value of B minus L, well, it's certainly not 0, but it's tiny compared to everything else. Okay, in other words, the universe is mostly hydrogen plus photons and neutrinos. Whoops, neutrinos. Duh. I left out neutrinos. All right, I was just thinking of protons and electrons when I was thinking about this afternoon. A lot of neutrinos out there. Of course, it could be that the neutrino number is 0. It could be, as many neutrinos as antineutrinos. So I haven't thought about this very much. But in any event, there might be it may be that there's a gauge field coupled to B minus L. And, but since baryon number and lepton number are anomalous, that means that maybe they're not really conserved. And that led Glashow and Georgine to think about proton decay this was actually back in the 70s. And this was one of the decays that they said might occur. And a search for this decay led to serious advances in neutrino physics. The reason is that they made a huge underwater detector with enormous numbers of Cherenkov counters and photoelectric detectors and so forth. And they were looking for this decay, and what they saw were neutrino interactions. So they've done a lot of neutrino physics with these proton decay detectors. But they didn't see any proton decay. And now the lifetime of the proton is greater than 10 to the 33 years. Notice that this decay respects B minus L. B minus L here is +1. B minus L here is minus 1 because lepton number of the electron is -1, but the positron is +1. And so that's actually a possibility. Now, one thing that we need to understand is why it is that baryon number and lepton number are so big. In other words, if you had a universe that was totally symmetric and you had some sort of big bang and then an era, inflation and then an era of radiation, you'd expect that particles and antiparticles would annihilate, and so you'd have equal numbers of protons and antiprotons, or quark, antiquark, leptons, antileptons, and these guys would all be zero. And so in other words, that the question is, how is it, not that B minus L is big, but how is it that B and L got so big? And so Sakharov, let me spell his name right, back in 1967, which is quite a while ago, showed that you could have, that if the physics satisfied three conditions, you might be able to generate non-zero baryon number, non-zero lepton number. And the first condition was the baryon number wasn't conserved. Well, we just realized that baryon number is anomalous, so it's reasonable that it not be conserved. The second consequence was, the second requirement is the charge conjugation shouldn't be conserved. Well, we know charge conjugation symmetry isn't exact. And he also said, well, CP shouldn't be conserved. Now, he was saying this only 3 years after CP non-conservation was discovered by Fitch and Cronin in kaon decays. And then the third thing was that you had to have a period in which the universe was out of equilibrium. Okay, so now I'm up to maybe 6 de Blasios. So you want the universe to be out of equilibrium because otherwise things might just go backwards, and you'd erase whatever baryon number or lepton number you had created. However, if you take the standard model and you try to estimate what the baryon number and lepton number would be, or let me just, yes, hi. Do you take UNM insurance?
I sure don't, and I'm not a physical therapist, I'm a massage therapist.
Oh, okay, thanks a lot, bye. My wife told me physical therapy won't show what you call that one. Okay, in the standard model, you try to do a quantitative calculation using normal cosmology present, as inspired by the CMB and the precision cosmology and so forth. You don't get enough baryon number generation or lepton number generation. So you need some physics beyond the standard model to give us the amount of baryon number and lepton number that we actually see in the universe. Yeah, it was 79, this Fujikawa paper. And in fact, this Fujikawa paper, as I said, it's rather, I thought of maybe trying to go through it in class, but I think it's pretty hairy, so maybe I'll put it on the website, but let it go at that. However, it is a very well-written paper, as opposed to being as hairy as possible with as little content as possible. This is as much content as possible with as little hair as possible. So he did a marvelous job writing that paper. It's a phys rev letter, and it's not even 4 pages. It's 3 plus epsilon pages. And yet it's quite clear. It's still deep and difficult to understand, but modulo that, pretty clear. Okay, I'm not sure of what to do at this point. I don't want to follow the rest of Schwartz's book because he is a professional QCD person, and the rest of the book is incredibly elaborate QCD stuff. So I think I'm not going to do that. So the question is what to do. And we've got a situation here in physics where we know there's something beyond the standard model, but we don't have any idea what it is. Most of the high energy community is convinced that it's supersymmetry. There's been no evidence for supersymmetry so far, but who knows? In a couple of months, there may be evidence for supersymmetry. So one thing I could do is start talking about supersymmetry. Another thing I could do is talk about superstrings, although I don't know. I know more about supersymmetry than I do about superstrings. But so maybe what I'll do next week is the first lecture will be supersymmetry, and the second lecture will be some supersymmetry and some superstrings. Is that? Oh, I forgot about grain unification. I should say something about grain unification. All right. So I'll try to do all three, because we don't know if grain unification is true either.
I guess I have more of an interest in supersymmetry than strings.
If we have to drop one, let's drop strings.
Yeah, I would suggest that.
Okay, all right, fine.
Doesn't one do one
I already did strings to some extent in the Monte Carlo seminar. What Monte Carlos and strings have to do with each other is precious little. But, although, if you were trying to do, well, actually, I once did a Monte Carlo of strings, a long time ago, I never published. No mistake. But anyway. All right. Well, let me just do some of the grain unification then. What you've got is you've got this group SU3 of color. We know we have that. And we know we have an SU2 left. And then we have this U1Y. And we want to put that inside some group. And the idea that, now, the idea that Georgia and Glashow came up with was to say, well, this thing fits inside SU5. And what they did then was this was the mid-70s, and so it was either before or shortly after the charm quark was discovered, or the J-psi particle was discovered, and whether it was interpreted immediately as the charm quark, I don't know. I don't remember. Whether that happened before they suggested this. But in any event, there was no people had not discovered the charm, or the top or the bottom quark, so the third generation was very much in the mist. And so they focused on one family. Now, I think this is a big weak point for grain unification, because what they're doing is the way they unified things, they wound up with a theory in which the Ward gauge bosons are coupled to B minus L and consequently could produce this. And then they said, well, because the proton lifetime, they didn't know it was 10 to the 33rd, they thought it was maybe like 10 to the 25th. And they said, well, let's go look for it. Why don't you guys go look for it? And so people did. And as I said, didn't find anything. And so the present view is that the mass of any of these gauge bosons, which I think they called X and Y, has to be in the order of 10 to the 16th GeV to be compatible with that. The lifetime, as I recall, goes down as the fourth power, I think, of the gauge boson mass. All right. Yeah, I guess so. I mean, if you have one propagator, it's squared. That's the amplitude. The probability then is the fourth power. Because it's the square of the amplitude. Yes, question?
What are X and Y?
These are the gauge bosons that couple to the generators that mediate transitions between quarks and leptons. So, for example, what they did was they took one generation. Now, how many particles were in one generation? Well, in the strict standard, this was before neutrino masses were established experimentally. So they took the neutrinos as massless. So they said, okay, we just have a left-handed neutrino, and so we have 15 particles. So they put it into a 5 and a 10. And the 10 was a 5 by 5 matrix that was, I guess, anti-symmetric. I didn't think I'd be talking about this today, so I haven't really prepared this. I think what they did here was they took 3 quarks. That's right. All right, let's see if we can do it. U red, U blue, U green, nu E. So this might have been, might with a capital M, okay? This might have been the 5. And then in the 10, they had the down quarks and all the other stuff. And I'm not quite sure where things went there. We're mercifully out of time. All right, well, I will, next time, yes.
This is a simple question. When you say grand unification theory, what are we unifying? I mean, what is the scope of that?
Okay, what's unified here is that we have one gauge group.
Okay.
And we can imagine that at very high energies, all the gauge bosons are massless, so we have perfect symmetry between up quarks and neutrinos and electrons. They're all perfectly symmetrical.
Okay.
And so we've got many generators of this because you've got SU5. So let's see, for SU3, you had a 3 by 3 matrix, 8 generators. Here you've got 24 generators, so there's 24 gauge bosons. So what do we have? We have 8 for A of SU3. We have 3 for the gauge bosons SU2, and then we have 1, I'll call it A, of hypercharge. So altogether that's 12. So half of them are missing.
Yeah.
And as I recall, they call them X and Y.
Okay.
And then the idea is that there are Higgs fields here, they invoke the Higgs mechanism. There are Higgs fields here that have mean values in the vacuum, not 246 GeV, but around 10 to the 16th GeV. And consequently, the other 12 gauge bosons get a very high mass, 10 to the 16th GeV. And well, I think SU5 has been ruled out for a variety of reasons. Witten introduced something nicer, which was SO10. Again, it's kind of weird that it's gone from unitary to orthogonal. But this included a right-handed neutrino. And then there are various ways that this can break down to the standard model. And this is a much more symmetrical one. But still, the idea that we have all these particles here at ordinary energies, and then we go up 10 or 12 orders of magnitude in energy, and all we've done is explain one family at a time. That isn't very good, is it? So that's a problem with this. Okay, on the other hand, the nice thing is that, and this was stressed by Georgia and Glashow, because you have a group here that's simple, there are no U1s. And just intrinsically, all the generators are traceless. So that means when you compute the charge, you get something plus something minus something equals 0. So that means you have some understanding of the charge. And in other words, there are these geometrical factors that come in and determine the charges. And so that's very nice. And, you know, when some future generations finally understand everything, then that'll be a feature that will be there. All right, why don't we quit at this time unless there's another question? Did you get your candy for the question?
No.
Oh, here.